In this video, we will talk about mixture of gases. Let us understand how is the mixture of gases different from mixture of other states. When we mix two solids or liquids, the total volume simply gets added. So, the total volume of each component may be V1 plus V2. But if we ask what is the volume of the first constituent, we will say it is V1. That is because the volumes remain conserved in solids and liquids. But this is not the case with gases. Let's understand it with this simple example. Let's assume we have a container of volume V. It is filled with N1 moles of a gas at temperature T. Hence, from ideal gas equation, we can say that the pressure experienced by the container walls will be this. Now imagine N2 moles of another gas in the same container at the same temperature. We can find the pressure of this gas again using ideal gas equation. What if these two gases were together? Can these two gases be treated independently? And if so, what will be the state variable of these two components of gases? Let's first answer the first part. Yes, they can be treated independently. We had already learned that the gases have no interparticle interaction and hence are completely independent of each other. A particle of this particular gas has no effect on another particle of the other gas or even another particle of the same gas. So what is its implication? We can analyze both components separately and apply ideal gas equation to each component. Let's first take the first gas. Though it's in a mixture, if we ask its volume, it will be the same as the volume of the container. This is the unique thing about gases. Their volume is the total volume available to them. And as other gas particles are very small, the total volume available to the first component is the same as the volume of the container. We can say that even about a single gas particle. If we focus on a single particle of this type of gas, its volume will still be the same as the volume of the container. Remember this concept. This comes straight from the fact that gas particles are independent of each other and are so small that they do not occupy any space. Now, if we are clear till this point, we can go about finding its other state variables. So, the volume for this component of the mixture is V. Number of moles are still N1 and the temperature is same, T. So its pressure will be what we have found independently using ideal gas equation. Now, we will do the same exercise for the second component. Its volume is again V, number of moles N2, temperature T, hence this will be the pressure. So, what do we finally get from this analysis? The total volume of the mixture of the two gases remains the same as the total volume of the container, and even individually they occupy the same space. The temperature is uniform in a mixture of gases. In our previous video, we had learned that even if the two gases were at different temperatures, in due time equilibrium will be established and complete mixture will arrive at a uniform temperature. The total moles of gases are N1 plus N2. So, we can apply the ideal gas equation to find the pressure experienced by the container. Will this be the total pressure of the mixture? Yes, it will be. So, we see that it does not matter if there is a mixture in a container or any particular gas inside a container because all ideal gases behave the same, independent of each other. And we can simply find the pressure just by knowing the volume of the container and the total number of moles of gas particles in the container. But this was the total pressure. What part of this is contributed by the first component of the mixture and what part by the second component? That would be simply this. And as you might already guess, the total pressure is just the sum of the individual pressures of these components. This is called the partial pressure. Let's sum up what we have learned in this video. Total pressure of a mixture of a gas is this. Partial pressure of each component of gas is this. Total pressure is sum of partial pressure of each component. Mathematically, we can find partial pressure of each component from the total pressure using this expression. Try to arrive at it yourself. It's easy. Now, this part should appear familiar to you. This is actually mole fraction of the first component of gas, and this is the mole fraction of second component of gas. This gives us Dalton's law of partial pressures, which says partial pressure of any component of a gas is total pressure into mole fraction of the gas. Remember this expression. We will be using it a lot for solving problems.